semester project for real-time systems. So the introduction and motivation for this project, something I noticed just in campus and where I live is that there's a large problem where people leave their clothes in the washer dryer because they don't know that the cycle is completed. So when I was thinking about solutions to how that problem could be mitigated, I came up with a project. And so the goal of this project was to create a current monitoring system for when a user scans an ID card. So like everyone on campus has a student ID card, in workplaces, everyone has a worker ID card. So we can easily associate a user with a current monitoring cycle, and then we can associate that ID card with contact information that we can then use to send a user a notification whenever the power cycle for their device is done. And so the system itself would monitor the power cycle and then notify the user when it's complete through the information on their ID card. So, like I mentioned earlier, this could be used in a washing machine or a dryer, but it also could be used in workplaces or other devices on campus with any shared appliances like coffee makers or 3D printers or and more. And so the project plan for this, the overall goal is to develop a current monitoring device that integrates RFID. So the first task was to enable the RFID reader to work with the interrupt with the ESP32 with an interrupt-driven approach. Then integrate the current transformer into the ESP32 system to monitor when current is flowing versus when it isn't, and then notify the user when current is flowing, meaning the device is on, versus when current isn't flowing, when the device is off. And so the overall goal is to notify the user in real time whenever a power cycle is done on their device. And so continuing on, the microcontroller that I decided to use for this project is the ESP32 because it's supported by the library with the current transformer and the RFID reader. And kind of into the scheduling aspect of it, the RFID reader should be interrupt driven so it doesn't take up more resources than it has to. So originally the plan was to use the IRQ pin on the RFID reader that I bought so that the reader could signal to the ESP32 when it should be ready to receive data, but the library for that RFID reader doesn't support the IRQ pin. And I also tried directly writing to the registers and that didn't work either. So then I investigated a little further, and then I determined that it wasn't that even if the IRQ pin was working, the microcontroller can't go into sleep mode and needs to prompt the RFID reader to update the IRQ pin anyway. So there wouldn't have been much advantage using the IRQ pin regardless. So eventually, I wanted to keep the interrupt-driven approach. So now there's a timer and the interrupt just triggers every 100 milliseconds to notify the RFID reader that it should check for a card. And then, of course, the current sensing should be polling based so we can obtain samples at regular intervals. And so this is a demo of the code for the project. Go to code. So we start by adding a few libraries to our code, the serial peripheral interface, the library for the RFID reader, an energy monitor library that we use for reading the current, and then a timer library that we use for the interrupt handler on the ESP32. So the first part here is pretty simple. We're just setting up NFC. The reset pin is on GPIO 5 and the SS pin is on GPIO 19. So we create an RFID reader on those two pins. We also have the ADC pin that is connected to the current transformer, and that's on pin 34. And then so we also create an energy monitor EMON1, which we'll be using to read current values later on. We also have two LEDs, a green one to notify when the LED is on, or excuse me, when current is flowing, and a red one to indicate when current is not flowing. We have a few flags. So the check card flag tells the loop whether an RFID card is present or not. So we initially set that to false. And then we also have a flag to know whether we are currently current monitoring or not. So again, the idea is current monitoring only starts when a user presents an RFID card, so we can differentiate between uh, so we can associate a user with the current that the current reading that is happening on a device. And then we also have a timer handler. The circular buffer we initialize here, which I'll get into more detail later on when it comes up. We have the interrupt handler right here. So again, we just very simply, we want to put as little in the actual interrupt itself as we can. So we just set the check card Boolean to true and then move on. In the setup, we begin the serial interface, initialize the LEDs, and then turn them off. We begin the serial peripheral interface, initialize the RFID card, and then we initialize the current sensor. So this 60.6 here is a calibration value. It's not necessarily super important, but it's just there so we can differentiate between when current is flowing and when it is not. And then we also have the timer for the interrupt. So the RFID part runs on an interrupt itself. And so that interrupt we want to run every 100 milliseconds. So we initialize a timer to trigger that interrupt. And then we go into the actual main loop itself. So the first part is we check if there is actually a card that was present on the RFID reader. If not, we just go through the loop again, but if there is, we jump into this code. So the very first thing we do is set the flag back to false, and then we check, see the new card that's present, and then read the data from the RFID card, and then print the unique identifier to the serial interface so we can differentiate between different cards. Then we know that we want to enable current monitoring. Again, we only enable current monitoring after an RFID card has been presented. So we do that. We set up our circular buffer. We reinitialize our circular buffer to 0 and say that it's not full. And then we make sure that both of our LEDs are turned off. And we then stop reading the RFID card. Then in the actual current monitoring section, again, we check to see if the flag for monitoring is enabled. And then here we use the energy monitor library to calculate an RMS current based off the values we get. So the current transformer, it reads an AC source, but the microcontroller can't read a negative voltage. So we instead need to calculate an RMS current based off of that. So this basically tells the library that we want to take 1,480 samples, um, and then calculate an RMS current based off of that. It's also important to note that the current that we get from this isn't the actual current that it's flowing, but it's more of a representation. In the demo video, you'll see that when current is not flowing, we get a value from anywhere from like 0 to 30, and when current is flowing, we get a value of about 380. And so since this project is mainly focused on determining whether current is flowing versus it's not, rather than actually reading the current, we don't need an exact precise current value. We just need to differentiate between on and off. And then going back to the circular buffer part, um, this basically just adds the value we just calculated to the circular buffer. So we have a circular buffer that stores 5 values. So we don't want to make determinations based off of just one sample. We want it based off a series of samples. So an erroneous reading or something like that doesn't impact it and cause a false change from on and off. So we check if the buffer is full, which means that we have 5 values in it. We calculate the sum of the values and then calculate an average based off of those. And then print that average value to the serial monitor. And then here, the 250 is a calibration value pretty much. So if we know that if the average is above 250 of the values we read, we have very good reason to believe that current is flowing, in which case we turn the green LED on and turn the red one off. We also know that if our average value is below 100, that usually means that current isn't flowing. So we turn the green LED off and then turn the red one on. And if neither of those are true, we just turn both off. And then the very last part is a 1 second delay before we get the next sample and jump back up to the top of the loop function. This is a demo of my semester project for real-time systems. So just to go over our test setup, we have the ESP32 microcontroller, which is connected to an RFID card reader, and additionally it's connected to this current transformer here that we have monitoring the current over one of the power lines that is going to our lamp that we'll be using to test with. We also have a burden resistor on the breadboard, which is used to calibrate the values which we get from the current transformer. Additionally, we have a green and a red LED, which we will use during the current sensing part of the project to indicate whether we are detecting current or whether we are not. So if we look at the serial monitor, we currently have a ready to scan card. So we are currently waiting until a user touches their card to the RFID card reader, indicating that they want to start monitoring current. And so this is the interrupt-driven part of the project. An interrupt will run every 100 milliseconds to check if there's a card present at the card reader. If not, it'll just check again 100 milliseconds later, or if it does, it jumps into the current sensing part. So if I scan my student ID, for example, we see that it reads the card and it starts pulling values from the current transformer. And so since the lamp is off, we have our red status LED, which is turned on, indicating that the device that we wish to monitor is not turned on. So whereas the card reading part is interrupt driven, this is a polling driven approach where we check values every so often and then do math on them to calculate whether we are detecting a current or whether we are not. So if we look here, we have a current value printed and then an average value printed. And so the way we do this is we don't just take one sample. Instead, we take 5 samples and store them in a circular buffer and then take the average of those values to determine what value we are getting from the current transformer. And from that, we make a determination whether the red or green status LED should be turned on and whether we are detecting current or not. So right now the lamp is off and our red LED is turned on. If we flick on the lamp, we can see that we have the green status LED turned on, indicating that we are reading a current going to the lamp. And if we take a look at the values, earlier we were getting values of about 0 to 20, whereas now we're getting values of 380. So we have a clear delineation between on and off, which we can use to calibrate to different devices. So for example, we can replace this lamp with something like a 3D printer. And so if you wanted to set up something like this where it sends you a text message when your 3D printer is done, you just have to calibrate the values so that it matches what the 3D printer is pulling.